Designing a heat exchanger comes down to one question. How much heat transfer area do we need? These units are everywhere: refineries, power stations, food plants, and chemical plants. Get the area right and the exchanger is compact and cheap, too small and it never reaches temperature. Our workhorse is the shell and tube, hundreds of tubes packed inside a cylindrical shell. One fluid flows through the tubes, the other flows around them through the shell. Hot oil enters the shell at 150 degrees and leaves at 80. Cooling water inside the tubes rises from 20 to 60 degrees, carrying the heat away. Step 1 of design. Find the duty, the rate of heat the exchanger must transfer. An energy balance on the water gives it. Duty equals mass flow times heat capacity times temperature rise. With 1.2 kilograms per second of water, the duty comes to about 200 kilowatts. Step 2. The temperature driving force that pushes this heat across the wall. It changes along the length, so the flow direction matters enormously. In co-current flow, the gap collapses near the exit and heat transfer stalls. In countercurrent flow, the streams run opposite, holding a strong gap the whole way. We capture it with the log mean temperature difference, here 74 degrees for countercurrent. Step 3. Real shell and tube units use multiple tube passes, not a pure countercurrent flow. So we multiply the log mean by a correction factor F. Read from charts for the pass arrangement. For our one shell, 2 tube pass design, F is about 0.91. Step 4. The overall heat transfer coefficient U, combining both films and the tube wall. For an all-to-water service, a typical design value is around 500 watts per square meter Kelvin. Step 5. Assemble the design equation. Duty equals U times area times the corrected log mean. Rearrange for the unknown. Area equals duty divided by U times F times the log mean. Plugging in our numbers gives a required surface area of about 6 square meters. Step 6. Turn that area into hardware by choosing a tube size and length. With 19 mm tubes, 3 meters long, 6 square meters needs about 34 tubes. A real design then checks pressure drop and adds a fouling allowance and iterates. But the backbone is always the same: duty, driving force, correction, U, and area. Size the area correctly, and the rest of the heat exchanger follows.